In this video, I'm going to talk about the behavior that we observe based on the elements, and we will explain this behavior using the electron configurations. This information is in sections 8.5 and 8.9. So the important thing about quantum mechanics is that it has explanatory power. So by that we mean that we have the periodic law, that we can make predictions, and then the quantum mechanics theory actually explains why the periodic law is the way it is. And so we see that chemical properties are periodic because the number of valence electrons are periodic. So here you have a periodic table with the quantum numbers superimposed over it, and so you have your n equals 1, 2, 3, 4, 5, 6, so that's the number that you see. That's your S. And then is L equals 0. P is L equals 1. D is L equals 2. F is L equals 3. And then we have our plus and our minus spins. So the chemical properties occur because of the way that these valence electrons fill out that outer shell. So let's start by talking about group 8A, or the noble gases. So unsurprisingly, these guys were the last to be discovered. So for a long time, the periodic table kind of stopped at the 7th row or 7th period. So the reason for that is these guys are totally inert. They don't react with anything. And remember, Mendeleev solved this periodic table before he even knew what an atom was, or proton, neutron, electron. And so these, they don't react very well. It took us a long time to find them. So let's talk about why they are so stable and unreactive. So they have 8 valence electrons, so they are absolutely stable. And so this results in the lowest energy that an atom of its principal quantum number can absolutely have. So the electrons, they can't lower their energy by doing any bonding, so they can't react. They don't really react because there's nothing to drive the reaction towards lower energy. And they also can't accept an electron. And so these are our little noble gases, and neon is something you're probably really familiar with. We see the neon signs. All of the noble gases glow very pretty colors, so you'll see different colors. You probably recognize some of these. Okay, so alkali metals. These guys are totally different. They are extremely reactive. So let's look at this. We see a 2s1. So they have one little electron. So they are one away from the noble gas configuration. And so if they give up an electron, they will then enter their low energy inert state. So they readily react to lose one electron. So these guys always form a positive 1 cation. Now, I want to point something out. It is a shortcut in speaking and thinking to say that an atom wants to be like a noble gas. Don't say that, because it's not true. Atoms have no consciousness. They cannot think. They do not have desires, wants. They just react due to the laws of physics and chemistry. Coulomb's law. So try to get away from that thinking of having desires or wanting or behaving like something else. These are extremely reactive because they only have one electron, and if they lose that electron, they then enter a very stable state. That's why they react that way. So we are going to watch a short little video showing how reactive these guys are.
So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium than the other 2 in terms of amount. You'll find that the reactivity is a little bit greater.
Okay, so that showed you a little bit about the reactivity. You saw that as we go down the group, the metals get more and more reactive, and there is a reason for that. We'll talk about that when we move in the next couple of videos. So when we talk about these alkali metals being highly reactive, that's because, again, they lose that 1 electron. So why are they called alkali metals? Well, it's pink. He said that it's making a hydroxide. So a hydroxide is a base. It's an alkali. Okay? So when they react with water, they make a basic or alkali compound. That's why they're called alkali metals. So alkaline earth metals, they're slightly less reactive than the alkali metals, but they're similar. They also form alkaline compounds when they react with water. So their valence electrons are 2 away from the noble gas configuration. So that means that if they lose these 2 electrons, they enter a stable configuration and they no longer react. So in other words, they readily react to lose 2 electrons. So these guys always form plus 2 cations. So you will see magnesium 2+, but you won't really see magnesium plus or magnesium 3+. They're always going to form 2+ cations because they lose those 2 electrons that are in their 5s or 4s or 3s subshell and become a positively charged stable cation. So you'll see that they don't react nearly as violently with water. Halogens are extremely reactive. This is bromine and iodine. It reacts with air to form this purple color really fast. And they are really reactive because you can see they are also 1 electron away from a noble gas configuration. But they are 1 away from a noble gas configuration in a different way than the alkaline metals are. They react to gain an electron. So this group always forms a negative anion, just a -1. So if chlorine accepts an electron, it will be 3s2, 3p6. It will have a full subshell and it will no longer react. So chloride would be always a negative charge. So you would see F-, but not F2- or 3-, or Cl-, but never Cl2- or 3-. So these are all elements that form ions with predictable charges. So our group 1A, 2A, aluminum is the only one in its group that forms a predictable charge. And these up here do as well. As you get into the transition metals and the d orbitals, there starts to be a lot more space and the ability to form varying charged ions occurs, and we'll talk about that in a minute. But notice that certain elements have ions with very predictable charges. So these are always a -2, this is a -1, this is a +1 and a +2. And this is because the element is either losing 2 electrons to achieve a low energy state, or it's gaining electrons to achieve that low energy state. So let's think about why transition metals might have variable charge. Okay, so these all have charges that we know, but these guys in here can have different charges. So let's take a look at iron. So you might run a review 3.5 of your textbook if it's been a while since you've taken 161. I'm not going to test you on this, but it might help make more sense of this. So let's look at iron. So our electron configuration of iron, 4s2, 3d6. So we can lose two electrons. So we could lose them from this 4s subshell. But then Why would we end up losing more? Well, let's take a look at the electron configuration and see if we can explain this. So if we lose 2 of the 4s electrons, that would make the most sense, right? So Fe2O3, these have a +3 charge, and the FeSO4, or iron sulfate, has a +2 charge. So the +2 makes sense. We lose the 4s here, and now we've lost 2 electrons, so a +2 charge. But for the iron oxide, which is rust, the most common form of iron I'm sure that you've seen in your lifetime, why does iron readily form a 3+ charge? Well, if you notice here, if it loses that one paired electron and then all of the d orbitals are now the same, that is energetically favorable. So iron will readily form a +2 charge by losing the 4s electrons, and then it can also form a +3 charge by losing one of its d electrons. So we can actually explain atomic and elemental behavior by looking at the electron configuration.